problem, we're asked to find the station elevation of the high point for the curve with a PVI at station 18 plus 95. So that's what we see on this set of design plans here. We're looking at the vertical alignment. So on the x-axis, we see the stationing. On the y-axis, we see the elevation. Anytime we're asked for elevation, we should immediately be thinking vertical curves, symmetric parabolic curves. We're going to need to come up with a parabolic equation for this. So here's our parabolic equation that we're going to customize for this particular curve. And we're also asked for the high point. So at that point, we should also be thinking we need to solve for the x value that's going to give us the high point location. So we can use this equation for that component. So these are the two equations we're going to use to solve this problem. And let's start taking a look now at the various components on our design plans. Grades are very important. So our entrance grade is known as G1, and that's going to be positive 3.6822. We're going to have G2, which is our exit grade, is going to be negative 4.0619. The negative sign is very important there, and we want to keep these in percent. So for G2, we're going to have negative 4.0619, making sure not to put that in decimal form. We want to keep that in percent. And for our G1, we're going to have that as the positive 3.6822. We also, an important component is the length of the curve L. And that's actually given to us here in this curve table. We could look also at the stations. So this is L, and we're going to put this in terms of stations. So 3.45 is the value we're going to put in there. As far as where the curve actually starts and stops, here's the PVC. Here's the PVT. And we've got the symmetric parabolic curve that connects those two. One of the components we know we're going to need to find is the elevation of the PVC. So let's go ahead and find the station and elevation of that PVC. In terms of the stationing, we're going to take the PI station, 18 plus 95. That was our reference point that we were given for the problem. We're going to subtract off half the length from that station because it's L over 2 between the PVI and the PVC. So it's going to be half of 345 feet, or 1.725 stations, or 172.5 feet. So we're going to take 1895, subtract off the 172.5 feet, or 1.725 stations. And we're going to get a station of that PVC of 17 plus 22.5. To find the elevation of the PVC, we're just going to use simple geometry. We're starting at the elevation of 646.32, and we're going to go down the slope of G1 3.6822% over a distance of that 172.5 feet, or 1.725 stations. So the way I would write this down is to find that elevation of the PVC is equal to the elevation of the PVI, 646.32, minus half the length. I'm going to put this in terms of stations. As I just said, 3.45 divided by 2 is 1.725, multiplied by that slope, 3.6822. And we're going to get an elevation for our PVC of 639.968 feet. So that's the elevation of our PVC. That's what we're going to put into our parabolic equation. So now we have G2, G1, we have L, that was a given. X is what we're finding. X is the horizontal distance starting from the PVC. We've got G1 again in the second term. X is what we're going to put in. And now we have our PVC elevation. So now we can create our parabolic equation. So Y equals G2 minus G1 over 2 times L. So that's going to give us that A term of negative 1.122 times x squared plus G1 times x, or G1 is 3.6822 times x, and then plus our PVC elevation, that's the 639.968. So that's our parabolic equation. So any value of x from 0 up to the length of the curve, which is 3.45, we can use for our parabolic equation. We can't do anything outside those bounds. So we're bounded from 0 to the length, putting that in stations. The other thing we need to find is our x distance to the high point. It's also called x of m. Sometimes you'll see that notation. So it's negative G1 times L over G2 minus G1. So if we do that math with our given components, we're going to get a value of 1.64. That's 1.64 stations from the PVC is where that happens. We were asked for the station and elevation of the high point. So we're going to add this x of m to our PVC station. The PVC station, remember, was 17 plus 22.5. We're going to add those together. And so for the high point, the station is going to be 18 plus 86.54. So this is one of the answers that we're asked to solve for. For vertical symmetric parabolic curves, vertical curves in general, the high point is going to be on the side of the PVI with a flatter grade. 3.68 is flatter than 4.06. So we do actually expect that high point to be to the left of the PVI, and that's correct. 1886 is before 1895, so that works out there. Another thing, we should also have some idea before we start calculating the elevation, we can read off this design plan approximately what it is. And it looks like we're somewhere in the range of 643. And so I'm going to expect some value around 643. If I don't get something there, I probably made a mistake with the math, and I'm going to take a closer look and see where I went wrong. So now I'm going to use the parabolic equation. I'm going to plug in my value of x. So it's y equals negative 1.122. Our x here is 1.64. So 1.64 squared multiplied by that a component plus 3.6822 times our x value again of 1.64. And then plus our PVC elevation 639.968. So it's this. Now we can find the high point elevation. So just working that math out, and we're going to find an elevation of 642.99 feet. And so that's the other component we were asked for, the station and elevation of the high point. And it tracks, it does work out. 642.99 is right around that, what we expected of 643 that we're able to read off the graph. So this is the information for the curve. We're able to answer the high point, station, and elevation for this curve of interest using the fundamentals of symmetric parabolic curves.